Hi, everyone. If you're watching this video, I guess that means you saw my email and you're aware that section on Tuesday has been canceled. This video is serving in its place. In addition to that, my office hours have moved later in the week this week, just to give me some breathing room for qualifying exams. So that's going to be Thursday and Friday. The times are slightly offset. Hopefully that'll help people in different time zones. But yeah, I'm assuming you guys will have more questions about homework by that point in the week, so feel free to stop by. That said, I'll also have math lab on Thursday, and we'll also have section on Thursday. Right, those are not changed. The only things changing are Monday and Tuesday. So yeah, Thursday is going to go as planned. We're going to have a quiz. I sent you guys out an email with some pointers on which sections to look at. So yeah, what we want to do today then is go over the end of chapter 14, the beginning of chapter 13. So chapter 13 is getting into some calculus-y stuff. Chapter 14 that we finished last week, I guess, was talking about cardinalities and the Cantor-Schroeder-Bernstein theorem, which gives you nice relationships between injections, bijections, and cardinalities of sets. So let's see here. I don't think I need to go over many definitions. Sorry, my mouse just died. Give me 1 second. All right, slightly better. I don't think I need to go over many definitions, but these will be uploaded if you need them. So I suppose one important one that we'll touch on towards the end of this video is the definition of a limit. Kind of just looks like a mess of symbols when you see it for the first time, but there's some nice graphical depictions you can draw. If you guys want some extra help with that, let me know during office hours. And we'll do a little proof related to this soon. Yeah, and other than that, there's a bunch of important theorems about, actually, I will highlight some of these because they're good to know. Any set is smaller than its power set. Smaller in the sense of cardinality. So in particular, that gives you things like the natural numbers may be countable, count of the infinite, but the power set of the natural numbers is something greater. Actually, sorry, I have a typo here. It's good I talked about this. So it's supposed to say equal to the cardinality of R, which is Aleph1. Cool. Yeah, so taking power sets lets you ascend this like infinite ladder of infinite numbers, which is kind of weird. You can keep going on that chain and you'll keep getting bigger and bigger infinities. And then we also have some important stuff for comparing sizes of infinite sets. So hopefully we're used to this by now. Stuff like the set of all even integers is equal in cardinality to Aleph naught, which is the set of all natural numbers or the set of all integers. Right? They're all countably infinite. You can form bijections between them. And then a couple other important things like, I don't think we've proved this in the general case yet. I believe the professor showed this example that you can form a bijection between these two intervals on the real line. In fact, you can form a bijection between like any intervals you want, as long as they're not degenerate. When I say degenerate, I mean, sure, you could write concrete. sure you could write the interval from 2 to 2, the closed interval from 2 to 2. That's the set of all numbers, all real numbers that are between 2 and 2. Of course, that's just going to be 2. So I guess I would call that degenerate because it's a weird example. Any other interval you write is going to have uncountably many real numbers in it, regardless of whether it's closed, open, half closed, as long as it's not one of these weird cases where it's a singleton or it's the empty set. You can always form a bijection between the two sets. Maybe hard to write down explicitly, but should be possible. And then we have the triangle inequality, which we'll play around with in a sec. So warm up, we did something like this, I think Thursday of last week, where instead we were dealing with 0, 1 cross n. This time we're dealing with 0, 1 cross r, and our claim is it's uncountable. I'll quickly show a proof of this. We'll say note that if I just took the set 0 cross r, that would be a subset of this. If you don't believe me, please do fill in the details, but the important thing is the set containing 0 is a subset of the set containing 0 and 1. And so taking the Cartesian product with R retains that subset relation. So I'll say note that, and note one other thing, that the cardinality of this set, 0 cross R, is exactly equal to the cardinality of R, because there exists a bijection between them. So I'll just write that out formally. There's a bijection from 0 cross R onto R. Or you could go the other way if you wanted to. Right? Bijections can go both ways. But we'll do it this way. And I'll say in particular, how would we define it? Well, I mean, the idea isn't too complicated. Instead of saying f is defined, I'll say f can be defined. Because there are a bunch of correct bijections you could write. This is just one of them. F could be defined as, well, take any ordered pair, 0, comma x. Maybe I'll put it in parentheses like that, so you really recognize it as an ordered pair, namely an ordered pair living in this set. Right, so the first coordinate has to be 0. The second coordinate can be any x value in the real numbers, any value of x. And the most obvious thing to do if I want to spit out a real number is just spit out x. And maybe it's worth talking about why it's bijective, just really quickly. Injective, we usually write down, suppose f of one thing equals f of another thing. When I say thing, I mean element of your domain. So in this case, an ordered pair starting with 0. Well, if those are equal, what does that mean? Well, let me just plug this into the formula here. F just spits out the second component, the second number. Right, so this is x1, this is x2, they're equal. Bam, you got injectivity. Surjectivity is similarly quick. Maybe I'll let you guys fill in the gaps for surjective, or I'll fill them in myself and then upload it to GouchoSpace. But the important thing is to note that this gives us something quite nice. This tells us that R has the same cardinality as 0 cross R. And that cardinality must be less than or equal to the cardinality of the set we were concerned with. That follows from this. Since one is a subset of the other, there's an injection from 0 cross R to 0, 1 cross R. If there's an injection, it means that their cardinalities have this nice inequality between them. And there you go, that's all you need, right? This is saying the cardinality of the set we're talking about is bigger than the cardinality of R, which is exactly the same as saying it's uncountable. You could even bound it above if you wanted to, right? You can even make a further argument and say something like, this is less than or equal to the cardinality of R cross R, because this is a subset of R. And maybe you guys know by now, well, that's like R2, but R2 has the same cardinality as R. So in fact, you can bound it on both sides by Aleph1 and show that the cardinality of this set is exactly equal to the cardinality of R. But maybe that's overkill. Anyway, let's try something else out. This one is a pretty challenging problem. It tests your understanding of set theory and functions and injectivity and surjectivity and cardinality all in one. So I figure this is good practice. Actually, it's good to try it on your own, because it's not one of the types of proofs that you can follow your nose and get to the right answer. Unless your nose is very clever and you've seen a lot of things before similar to this. So I've already sketched a picture. The idea is I'm defining a collection of sets, or sorry, a collection of functions. This collection of functions we're calling curly f, and it's composed of any function that maps from the natural numbers to the set 0, 1. Right, so what I've drawn here is a function that evaluates to 0 or 1, depending on what natural number you input. And I don't know, maybe I'll just say this is a function phi. You'll see why in a second. And this goes on forever, right? My domain is all the natural numbers, so I go on forever. And the claim is, if I actually list out all of these functions, think about like, all the ways I could light up this infinite strip, then actually there are uncountably many functions of this type, which feels weird because, n is countable, right? The natural numbers are a quintessential example of countably infinite set. So how on earth would, just thinking about functions from the natural numbers to a particularly small set, just the set containing 0 and 1, how does that kind of explode and give you something with the cardinality of the real numbers? And I'll say it has something to do with like power sets, but we'll see as we go. So I've written here that if I want to show that the cardinality of this set is equal to the cardinality of R, that amounts to finding a bijection between my set and R. But I'm actually going to say, if we're dealing with subsets of the natural numbers, maybe we want to find a bijection to the power set of the naturals, right? We know that these two things have equal cardinalities, so that would be just as good. That's a trick we'll use from time to time. If you can't think of a bijection to one kind of set, maybe you'll find a bijection to a set with the same cardinality. And in this case, we know these two do have the same cardinalities. All right, so given that hint, how could I possibly proceed? Well, let's try defining something. So I want this function f to go from curly f, power set of naturals. And what that means is if I'm given some phi, which belongs to this set curly f, I want it to spit out some subset of the natural numbers. Right, so what I'm going to say is f of phi has to equal some subset of the naturals. Let's say all n in the natural numbers such that something. But I'm kind of building this up as you might think of it on a test or something. Well, hopefully, I don't know if a problem this difficult would be on a test, but anyway. The first thing that's weird is, we're plugging a function into a function. That's something you'll get used to in time. It's probably going to make you uncomfortable right now. But it's allowed. I mean, functions can map from any set to any other set. Turns out the set we're starting with is a set of functions. So yeah, you have to plug a function into it. Sorry if that's weird. And I want to spit out a subset of naturals. What subset could I possibly spit out to make this a bijective function? Well, looking up here, I mean, we're already dealing with the natural numbers. We have some like points scattered in the plane in a nice way. Maybe you look and you think, oh, this is a nice subset of the naturals, right? Everything that's highlighted here, everything that mapped to 0. Right? Or maybe this is a nice subset of the naturals. In particular, 2 and 5 both map onto 1. So 2 and 5, that's a subset of the naturals. So I don't know, we're just making guesses here and trying to be a little creative with it. Let's go with that. Let's say the subset I want is all things that map onto 1. I didn't make myself much room there. Apologies. Set of all natural numbers such that phi of n equals 1. Hopefully you agree with me then that that's a subset of the naturals. So it's an element of the power set of the naturals. And the claim is this is bijective, right? And by now we're just kind of feeling around in the dark and hoping something works out. So let's check that it does. So we'll check injectivity, and injectivity is going to be a bit challenging. Luckily, surjectivity is going to fall in place real quick. So injectivity, well, I want to say the function evaluates to, I want to like take two elements of my domain, call them phi and psi, and suppose that their function values are equal. Okay, again, weird. You're plugging functions into functions and getting sets out. But stick with me. So phi and psi are just in this family F. What does this mean? Well, we have the definition of F of phi, right? It's this set. So I might as well write that down. That means this set of all natural numbers such that phi of n equals 1 is equal to, same story, just plug psi in here. So it'd be the set of all naturals that have psi of n equal to 1. So those two sets are equal, and let's just have a shorthand. Let's call them A and B. Okay, we know A and B are equal, so we'll note that A is a subset of B and B is a subset of A. That's our definition of set equality. We'll see how to use that in a second. So what do I want to do? So let's write a note to ourselves. Our goal. We started with two elements of our domain, said they mapped onto the same thing in the codomain. Their function values are equal. That means I want to show these are equal. I want to show phi equals psi. But phi and psi are functions. So if I want to show phi equals psi, I really want to show phi of x equals phi, I guess I should use n because we're dealing with naturals, equals psi of n for all n in the naturals. That's my goal for injectivity. So let's keep that down here. And I'll say now, I'm sort of going to break into cases. I don't exactly know what's going to happen with these function values. But I do know that they only have two options. They're either going to be equal to 1 or 0. Right? Like in this function up here, right? My function was either evaluating to 0 on certain inputs or evaluating to 1 on other inputs. So, all right, let's just say n is an A, which is to say phi of n equals 1. That's the defining characteristic of the set A. It means phi of that number equals 1. Then I'll say, since A is a subset of B, this implies n is in B. Right? Taking n and A gives me n and B because A is a subset of B. But that's the same as saying psi of n equals 1. Okay, that is golden because if phi of n is 1 and psi of n is also 1, then they're equal to each other. Right? Phi of n is psi of n. So I could call this case 1 maybe. And then I'll put a case 2 here. I'll say on the other hand, if n is not in A, then what do we get? Well, if n is not in A, that means phi of n is not equal to 1. But what's our only option then? These functions map onto a very restricted codomain. It either outputs 0 or it outputs 1. If I'm saying it can't be equal to 1, it must be equal to 0. And then I'll say since, well, let me erase some of my highlighting. It's getting out of hand. Since B is a subset of A, you might remember actually that this implies the reverse inclusion for complements, n minus A contained in n minus B. You can draw a nice Venn diagram for that. I encourage you to do so. Okay, so if n is not in A, it has to be in n minus A, the complement of A. Well, that means it's in the complement of B. So we'll say since B is a subset of A, this implies n is in the complement of B, so it's not in B, and that gives us psi of n equals 0. Again, really nice. Both of them equal 0, so they must be equal to each other. Right, so that is actually our goal complete. There are only two possible cases, and in both cases, these two things are equal. So indeed, phi of n equals psi of n for all n in the natural numbers, which is the exact same thing as saying phi is equal to psi. Technically, you're supposed to say the domains of the function are also the same, but that was given to us. So we get set equality. Function equality, sorry. Right, so we started with this, we ended with this. That means injectivity holds. Cool. Surjective is super quick comparatively, so I might as well finish it off. Surjectivity means, well, recall where our function is mapping. F is mapping to the power set of n. So we're going to pick some element of the power set of n. I call it x, why not? And if you don't like talking about power sets, all that means is x is a subset of the naturals. Our goal is going to be to find some function phi from n to 0, 1, such that f of phi equals this set x. Okay, so let's actually define it. Again, you have to be a little creative here, but this one's maybe a bit easier. I want a function from the naturals to 0, 1, so that it, when I plug it into this function I started with, it actually spits out the set x. So the most natural thing to do, I encourage you to sit down and spend some time with this, but the most natural thing to do here is use the indicator function. I forget if that's a term I've used before, but the way you define that is you say, well, phi of n can be one of two things. So it's a piecewise function. We want it to either be 0 or 1, right? So let's say it's 1 under some circumstances, 0 under some other circumstance. I'll say 0 otherwise. And the question is, what goes here? And I want this function to evaluate to 1 under what condition? Well, the condition better involve this set x. Otherwise, how on earth are we going to get this nice relation? So, I mean, you might think to yourself, well, it has to involve n, it has to involve x. So just say if n is in the set x, output 1. Otherwise, output 0. That's a nice binary condition. Either n is in the set x or it isn't. So that'll guarantee I'm always outputting 0 or 1 here. And now let's check this thing that I wrote in my goal. Let's check that f of phi actually equals x. Just erase that. F of phi equals, again, just go back and look at your definition of f. F of phi is this thing. So let's write that down. F of phi is the set of all n such that phi of n equals 1. But hey, we have a definition for phi of n now. So what does it mean for phi of n to be equal to 1? Well, it's only 1 if n is an x. So this is actually equal to, keep this the same, phi of n equals 1 means n is in X. But what is this set? Well, the set of all natural numbers that are in X is just the set X. So it is surjective. Right? Whatever set X I start with in my codomain, my function spits it out for some choice of phi. All right, so that's my torture done for the day. Let's try some other stuff. All right, here's one from the section on the triangle inequality. I kind of like this one. I used it recently or something similar to it in like qual prep. So why not? So let's say we have here, I'm calling it a sequence of real numbers. You guys know what sequences are from calculus. I guess we haven't formally defined them in this class. Just say it's a subset of R. That's all a sequence is. It's just a collection of real numbers that you put in a nice order. I guess sequences allow repeats. So that's not ideal, but whatever. Not important for us. Here's our claim. So if we have this sequence of real numbers and we know that this inequality holds for whatever value of n you want to plug in. So really this is saying that you're imagining a number line and here's x1 and here's x2. Well, they should be within 1/2 of each other. So this distance is less than 1/2. But then, you also have an x3. And that better be really close, actually. That better be less than 1/4 away. And then an x4 better be even closer. And so on and so forth. So the distance between these successive elements of your sequence is decreasing. Then apparently, no matter what n and m I give you, no matter what, like, those are the indices for the sequence, but really that's just saying no matter what pair of elements in the sequence I give you, they're always going to be at least, or at most, 1 unit apart, which hopefully feels right. Right? If I took x1 and something really far off here, they're never going to be more than 1 apart. So let's prove that. And let's actually play around with this quantity. So I'll just write a sequence of equations down. Xn minus xm. All right, let's start by saying we want n and m to be natural numbers. So let n and m be natural numbers. And suppose, without loss of generality, that n is less than m. Without loss of generality means I could easily switch it, make n bigger than m, but the argument would be the same. I'm going to ignore the case where they're equal, because if they were equal, you would get 0 here, and that would obviously be satisfied. But anyway, suppose without loss of generality that n is less than m, then we can write didn't leave much room for myself, did I? Xn minus xm. We want to prove this. We want to prove this quantity is less than 1. So I don't know, what could I do? I could apply the triangle inequality. And here's a cool way, maybe you haven't seen it applied. Normally you apply the triangle inequality and you say, okay, I go to some value y, that's some intermediary value, and kind of split it into two chunks. But you can keep going. You can keep applying the triangle inequality, like I could apply it here now, and then keep going and keep breaking it up. So, whoops. One thing we could do is we could write this as, well, what about the distance between xn and the very next term in the sequence? And then take that term and look at its distance to the term after it, and so on and so forth. And then eventually I get to the end, the distance between the terms m minus 1 and m. Okay, so I did like a bunch of applications of the triangle inequality in one step. Totally valid. Right, all this is saying is it's faster to walk from point A to point B than it is to walk from point A to a bunch of intermediary steps and then eventually get to point B. And then what can we do? Well, we have an assumption about subsequent terms in the sequence. So like this, must be less than 1 over 2 to the n. Maybe I'll put that here. And how about the next term? N plus 1 and n minus 1. I mean, same story. I just have to replace n with n plus 1 here. So this would be less than 1 over 2 to the n plus 1, dot, dot, dot. This final term would be 2 to the m minus 1. Okay, so maybe I write this as a sum. Why not? Maybe I say that's k goes from n to m minus 1, 1 over 2 to the k. Cool. But finite sums are, finite sums are usually nice, but looking at this, you might think it's a sort of like a geometric series. And we know from calculus, if it were an infinite geometric series, say I started at k equals, I guess you usually start at 0. No, yeah, 1 is fine. If I start at 1 here, this is 1/2 to the k, then what do I get? Let me scoot this down. Well, that geometric series has an exact value that actually equals 1. And so lo and behold, we started with this quantity, same quantity that was mentioned here. And we eventually showed it was less than 1, which is exactly what we wanted. And maybe that's what you thought of when I drew this picture. It looked like a sort of geometric or like sub-geometric series. There you go. It's a nice application of the triangle inequality. Cool. All right, last one I think we'll do is this one related to limits. So what I want to do is run up here and grab our definition that I alluded to a while back. This is our definition of limit. So I'm just going to plop it here because I suspect most people have not memorized it, at least not yet. And we'll put it in red. Make it look intimidating. Okay. That's our definition of a limit. And we'll just take it for what it is. At the moment, we'll think of it as a smattering of symbols and try our best to work with it. All right, so strictly from a proof standpoint, not thinking about intuition here as we might want to, but sometimes it's good just to think about the logic behind it. If I want something to be true for all epsilon greater than 0, should always start by saying, pick some arbitrary epsilon greater than 0. All right. I have to show there exists a delta greater than 0 with some property. So what I'll write next is I'll say choose delta to be equal to blank. Don't know what I'm going to write here yet. This usually comes to you once you've written the rest of the proof down. So these sort of limit proofs are a bit backwards. It takes some getting used to. But anyway, that's our goal. Our goal is to find delta so that this works. And what is this? Well, this is an implication with an assumption on the left and a conclusion on the right. So, I mean, if there's an assumption on the left, let's assume it. Assume this holds. Of course, I have to pick what C is. And if you look back at the definition of a limit, C is the value that X is approaching. So maybe I'll highlight that in red or purple. C is -1 in this case. So I'm going to say assume this holds. Again, we don't know what delta is, but we'll write it down anyway and fill in the gaps later. And here I'll just say for some X. In the real numbers, ran out of space, but we didn't exactly tell you what X was, but we're just saying this holds for some X. So assume that's true. Our entire goal now is proving this. And it's important to highlight one other thing here, namely, what is this value L? I encourage you to stare at it for a second and try to figure it out from the definition. Pause the video if you have to. And here we go. L is precisely the limit, right? We're saying the limit equals 2. So we're using L for limit. There are enough symbols floating around here that we don't want to make it too difficult. All right, so we'll say then. This is the thing I want to mess with. F of X minus L. Well, L is 2. Maybe I'll even write it out like this. F of X minus L is what? Well, we know what F of X is. It's this function, 4x plus 6. We know what L is. L is 2. So just plug everything in. What does this look like? Well, that's 4x plus 4. And you might look at that and think, oh, that's nice. I could probably simplify that. If you don't think that, what you should do is you should look here and be like, well, I'm assuming this thing is true. I should always use my assumption somewhere. Maybe I'll rewrite this in a nicer form. Instead of saying minus -1 here, I'll just say +1. So look at that. X, the absolute value of X plus 1 is in our assumption. And if I pulled a 4 out, the absolute value of X plus 1 is also here. So that seems like it should be useful, right? This tells us we can just write this quantity is less than, okay, I got to keep the 4, but the highlighted part is less than delta. So that's less than 4 delta. What good is this? Well, again, keep in mind our goal. Whoops, I erased our goal. Our goal is to show this. Namely, the important part, I wanted this thing to be less than epsilon, not less than 4 delta. But I haven't chosen delta yet. I could make delta a really smart choice. Maybe you think, ooh, if I pick delta to be epsilon over 4, then this would be 4 times delta, that's 4 times epsilon over 4. The 4's cancel, I get epsilon. Ta-da. Right? F of x minus L less than epsilon. Exactly what we wanted. And that's how it goes, right? We didn't know delta until we got to the end and deduced this is the value we needed for delta. We needed it to be 1/4 of whatever epsilon was. After some practice and getting used to this stuff, you'll realize, oh, it's actually because the slope of the function was 4. And what's happening here is, okay. Try to draw this kind of well. It's probably going to get butchered. 1, 2, 3, 4, 5, 6. That's our function. 4x plus 6. We're asking what the limit is as x approaches -1. -1's here. Actually goes up to here. The limit just turns out to be the function value. I mean, you guys know from calculus, if you have some nice function like this, you can just plug -1 in and ta-da, you're done. But proving it amounted to what? Well, it amounted to saying, so let's zoom in a bit here. It amounted to saying that if I start with some like neighborhood, right? So I've picked epsilon. And epsilon is going to be what I'm going to call it a neighborhood of the limit. Right, so the limit is supposed to be 2 on the y-axis. So I'm looking at 2 here. And I'm thinking, okay, let's look at some epsilon neighborhood of 2. It's 2 plus epsilon. It's 2 minus epsilon. And it turns out that the whole goal of an exercise like this is to figure out the corresponding delta neighborhood. So this was your value C. On the left here, this was like, okay, C minus delta. On the right was C plus delta. And it turns out, since it has a slope of 4, that's sort of like pre-image as you go down, it's going to be 1/4 of whatever you started with. So delta equal to epsilon over 4 is nice here. And you can use that as a trick in general. If you're dealing with linear functions, it's you might guess it's always going to be something like that, right? The slope, the reciprocal of the slope. Yeah, so anyway, that was just a sidebar at the end. The important structure of the proof is there. I can erase this now. All right, so that's all we want to talk about for today. Like I said, keep mindful of the new schedule. We are going to be meeting on Thursday. We are going to have a quiz. The stuff we went over today is pretty important, so make sure you understand it, at least most of it. And other than that, see you guys either on Thursday, or that's in section, or it's in math lab or office hours, whenever it may be. So yeah, let me know if any questions pop up. Otherwise, I'll see you guys later. Of course, my mouse stopped working.